Very much for the very nice introduction. Let me try and just set this up and let's see, can you actually see that?
Yes.
All right, perfect. So my talk is on adapting the toolkit of many-body theory to realistic material simulations. And the work that I'm going to present has been done over many years by many people, but I want to mention in particular Johnny Fay here, who was an undergrad student in my group, who did a lot of the complex analysis that I'm going to present, and Jianan Ye, who's a graduate student who's just about to graduate, who did a lot of the implementation of the real material stuff, and Sergey, who worked on a lot of the DCA stuff. And then in addition, some of the work that I'm going to present was also done in collaboration with Dominika Skitt, who's at the Michigan Chemistry Department. Now, let me start with a couple of really controversial statements. In condensed matter, all the equations are actually known very well. You have one of them up there. And so basically, we just need to solve them. And theory is essentially over. All we need is a large enough computer, and we're done. Second controversial statement is that in quantum mechanics, everything is exponential. Now, what does that statement actually mean? Well, because it's exponential, of course, we cannot make any progress. And therefore, if we want to make progress, we need to have a quantum computer, right? So somebody better give us a good quantum computer so that we can say anything about any quantum system. But what does it actually mean to be exponential? Well, typically that just means that as a function of some control parameter like the system size or the temperature or the inverse temperature or whatever, things become progressively harder and harder. So with all of this, it's actually not that dire. And especially when we look at realistic computation, then there's a lot that we can really do. And in a way, I don't need to show tell you that because you're experts on this, but it still pays to sort of just recap it. So computational tools for electronic structure and condensed matter and quantum chemistry and so on are really very old. They have been developed since the beginning of the computers and were often a motivation for developing computer. Density functional theory, as about half of you know very well, is really the workhorse of electronic structure theory. And there's a lot of stuff that works really well. Ground state lattice structures, phonons, solids with light elements, Fermi surfaces, band structures of the occupied part, of simple solids, all of that really works well. And I think one of the big achievements of this community is not just to make it work well, but to make it work well for everybody. There are numerous open source packages that are easy to download, easy to install, ready to use. Calculations are straightforward to the extent that we often do this now, even in undergraduate classes, as an example of how you can do a band structure calculation. Now, what would we actually like to do? The fact that we can do many calculations doesn't mean that these are the calculations that we would actually want to do. From a physics perspective, basically all bets are off when electronic correlations are strong, even for structure. Most of our experiments are done at finite temperature or, as a function of temperature as a control parameter. And we'd really like to be able to say something about temperature evolution of properties rather than just ground state. We care about phase transitions. Often those phase transitions have electronic components. We care about optical response functions and optical excitations. I have 3 experiments listed over here. We want to know about transport. And of course, none of this, or at least none of the experiments that we care about are really ground state property. Very often, we would also like to make a connection to the theory community and, talk to a theorist about competition versus coexistence, intertwining, interpretation in some sort of theoretical scheme, or even consistency with some sort of theoretical scheme. Now, that's the physics perspective that you often hear. I want to give you a slightly different perspective of how we would like to do calculations, and that is a perspective that comes from applied math. And any applied mathematician worth his salary will tell you that a good algorithm provides you not just with a number, but also with an error bound. It gives you an a priori and an a posteriori error estimate. And then with your a posteriori error estimate, you can then gradually go in and refine those solutions in the places where they're unreliable to become more and more reliable until you've reached, until you have a precision bound on your solution that is accurate within the precision that you care about. So results are always not just provided as a number, but provided with an additional uncertainty estimate that actually tell you whether you're supposed to trust that result or not. And so in the remainder of this talk, I would like to tell you about some progress that we're making towards methods of this type. I'm going to start with considerations for real materials diagrammatics. I'm then going to talk about the mathematical toolkit that we need for that. I'll show you a little bit how we can try and make systems systematically more accurate and systematically controlled. And I'll give you both a failed hierarchy and a successful hierarchy, and then I'll talk a little bit about future prospects and methodology that can get us towards that goal. Now, to lay the foundations, I want to go all the way back to weak coupling theory. And one of the things that I want to do here is use diagrammatic perturbation theory as a foundation for strong correlation embedding theories. Basically, we want finite temperature formalisms. So we want to be able to talk about phase transitions, about entropy and things like that. We want to have conservation laws and thermodynamic consistency. And we want to have an independence of the starting point that we're having in our perturbation theory. And that basically leaves us at fully self-consistent diagrammatics and rules out any sort of additional approximations such as quasiparticle approximations, quasiparticle self-consistencies, partial self-consistencies of various types, or other approximations. For the experts, for Vlad and Hanna in here, what you really need in order to do a successful finite temperature theory is a phi derivable theory so that you have conservation of energy momentum and other conservation laws. Unfortunately, with our current toolkit, finite temperature diagrammatics or fully self-consistent diagrammatics has to be done on the imaginary axis. The self-consistencies just simply don't work on the real axis. And that means at this point, we essentially have a program set for us by the 1960s. Let us take a system, choose a basis, evaluate the Coulomb matrix elements or the interactions in that basis, obtain a mean field solution or a Hartree-Fock solution, then evaluate all the higher order diagrams and close the self-consistency. And all of this is basically the diagrammatic many-body perturbation theory written down in the 1960s. So the question is, can we actually do that in practice? And of course, it turns out that this is remarkably non-trivial for a realistic solid, and that's essentially why it hasn't been done before. If you think of the energy scales that you have in your problem, typically you have multiple Hartrees, from going from your cores to your valence electrons. At the same time, you would like to resolve temperatures in Kelvin or even millikelvins. And that means that naively, you have billions of Matsubara frequencies that you need to resolve and store. You can solve that problem with efficient adaptive grids. Chebyshev and IR are some terms for experts here. You can do that both in frequency and imaginary time. And essentially with compressed adaptive grid, you can actually resolve these energy scales with something like 100 to 400 or so frequencies. Next problem is that when you look at the interaction tensor, just the Coulomb tensor VI/KL, again, I don't need to tell this to the electronic structure community over here. If you just think of a minimum of like 120 orbitals per unit cell, which is actually very, very little. Say you want to do a 4x4x4 grid, right? That already gives you 405 terabytes of storage. So basically, yes, we could principle do that, but it's certainly not something that is pleasant. And again, with a lot of numerical mathematics and adaptive technology and data science technology, compression and things like that, we can actually take these things, decompose them, and then compress them and actually get them to a place where we can work with them. Now, we still have the problem of actually having to be able to solve the computational problem, solve many-body perturbation theory. And, the computational scaling of these methods is at least n to the third, and more like n to the 5 for, second-order perturbation theory. And for that, we really just then need to go and get a large computer. And so here is an example. In this case, this is just GW and second-order perturbation theory, where you now take diagrammatic perturbation theory. Here you have a second-order diagram for a self-energy, and you express that diagram contraction as just a sequence of block-dense matrix multiplications.
So, Emanuel, just a question here before you go on. What my friend Mr. Howlett says is that, well, you only have so many orbitals where the interactions actually play a role. You can have many orbitals, but if you just calculate, for highly excited orbital, some orbitals which are not nearly high field, well, then the interactions play a very small role. So when you said 120, maybe that's a little bit pessimistic. So what do you have to say about that?
Well, okay. I can answer this in many ways, but the way that I would like you to answer is that you should really have a method that adaptively computes which ones are important and which ones are not, and gives you a control parameter based on precision. That's where you would want to be. That's not where the methods are right now. In order to get there, I think that, that's the fair answer. If that is indeed the case, and I'm not saying it's not, then your method better tell you so automatically and give you an error bound. We're nowhere near there. Anyway, so a major peculiarity of all of these diagram contractions, basically any diagram contraction, is that you can write these things as dense matrix multiplies or tensor contractions. And it just so turns out that tensor contractions are very data intensive, very calculation intensive, but not very data intensive. And so therefore, they're almost ideally suited for GPU calculations. And what you see down here is a typical high-end CPU, takes about 1 teraflop per second, costs about $4,000 or so. But when you go to the GPUs, then a previous generation GPU already gets you about 6 teraflops per second. That's one of those that you have on Summit. The current generation GPUs give you about 40 teraflops per second. By the next generation, these are the ones that are currently being installed at Oak Ridge on I think Frontier. I forgot what the machine is called. You have something like 100 teraflops per second for about 10K per card, with something between 4 and 8 cards per node. So you can now see that just with sheer brute force, you can get 100 teraflops per second per card, times a couple of thousand nodes or so. That gives you the computational muscle that you need in order to actually be able to perform these calculations in practice. Now, does that actually work? Well, here's an Oak Ridge demonstration. This is on Summit, in this case with first order perturbation theory, so GW, in the renormalized interaction, performed self-consistently, fully self-consistently. On top, you see a couple of scaling plots. I just want to show you the middle one, where you see that in practice, these calculations reach somewhere near 72% of theoretical peak performance. So of the theoretical performance of the machine, which is basically unheard of. These are extremely efficient calculations. Once you have that, there's a physical result that comes out of it. And you see that on the right, you see there blue and orange curves. Those are essentially different ways of computing energies, entropies, and specific heat. And you can see that in practice, these calculations are now thermodynamically consistent and conserving. And that shows you that indeed that diagrammatic perturbation theory is now solved fully self-consistent and independent of its starting point, and has converged to a nice finite temperature result. With that, we can now finally go and do some materials calculation. And what you see here is a spectral function, or the single particle excitation spectrum, or the band structure, if you want, of silicon. It is solved here on a 6x6x6 lattice within self-consistent GW. And as you can see, there is an indirect band gap. Now, let me see if I can get my mouse pointer back. I might have to, let's see if it actually stays. No, it doesn't want to stay. Anyway, you can see that here. There is an indirect band gap between the gamma point and somewhere between gamma and X. There's clearly a high degeneracy somewhere near the gamma point. You can probably make out some of the other bands, but basically they're, as a DFT person, you would not expect this, you would not accept this as a band structure. This is a little bit ridiculous. So you can see that by doing this finite temperature field theory calculation, we ended up with a nice finite temperature result, but extracting experimentally important information is actually very difficult. This was a problem that existed in the field for many years, and basically with an undergraduate student, we revisited this problem recently by just going back to the roots of complex analysis. What you saw here was a consequence of an ill-conditioned analytic continuation that is required in order to obtain the spectral function A of omega out of the Matsubara-Green's function G of I omega n that you see in the first line over here. The reason why this looked so bad was because the inversion kernel that you see at the bottom right equation over here is badly conditioned, and that ill conditioning requires you to go through all sorts of numerical tricks. Now, those tricks then lose a lot of the precision. Now, we realized that these functions have mathematical properties. They're so-called Neven-Linna functions. What that means in this context is that the imaginary part of the Green's function is negative anywhere on the upper half of the complex plane. And we also realized that none of our current methodology actually respects that mathematical property. So we went back to the literature of the 1910s, 1920s, and 1930s and dug out some of the methods that people used in complex analysis to interpolate Neven-Linna function. And now you see on the right the current state of the art of what you can actually do with finite temperature field theory data. Importantly, this is exactly the same data that gave you the spectral function at the top left, now with new technology at the bottom right here. And all of a sudden, you can actually see that there's a triple degeneracy at the gamma point. There's then a doubly degenerate band dispersing from it. There's clearly an indirect band gap. And in fact, you can resolve all of those other bands that are floating around both in the occupied and in the unoccupied part. This is a function, this is now a solution that is completely independent of density functional theory. It is a purely diagrammatic, self-consistent GW, so first order Hedian's equation solution that now satisfies all of the conservation laws and where all of the things are thermodynamically consistent. All right, with that, we have the toolkit to progress towards real calculations, but as a side effect of this, there's actually a couple of things that we can now do that were just unthinkable before. For instance, we can compute the Green's function on the Matsubara axis, analytically continue it, and get the Green's function on the real axis, which is related to the spectral function, which is plotted up here. We can also look at the Green's function by computing the many-body self-energy, analytically continuing the self-energy, and then running the Dyson equation on the real axis to obtain the same thing. And we can look at the related cumulant, which I'm not going to go into in too much detail here. Importantly, no matter what we do, we now have the precision to go back and forth with analytic continuation and with Dyson equation on the real and imaginary axis to permute these operations, and we're ending up with exactly the same function. That doesn't look that interesting unless you realize that most of the many-body calculations actually take the self-energy, strip out all of the off-diagonal parts, or even strip out all of the dynamical parts of the self-energy. That, for example, is done with the so-called quasiparticle approximation. And then you're getting a Green's function, just based on an approximated self-energy. Now, does that approximation matter? Well, we can go and just check it by taking our self-energies and truncating the off-diagonal parts. And what you see here in the middle is the fully interacting Fock matrix without the frequency-dependent self-energy analytically continued. Compare this to the left, you see a completely different band gap of this compound. And again, this is a weak coupling compound. It's just silicon. It's just a demonstration experiment. And on the right, you see what is typically done in LDA plus DMFT and other techniques, where you just have a diagonal self-energy that you continue that you then add to the band structure. Those things matter in practice. And if you don't get your band gaps right, this is one of the major places where you have to go look for it. Neglection of the off-diagonal parts of the self-energy. Anyway, so be careful with that. Let's continue to a little bit more realistic calculations. Next step, add relativistics to it. So especially when we're interested in heavy compounds, we would like to be able to do relativistic perturbation theory. In our case, that means not solving the Schrödinger equation, but solving the Dirac equation. We can do that in the so-called exact two-component formalism in the one-electron approximation. That is a very clever approximation that became prominent in quantum chemistry over the last couple of years that allows you to leave the two-body integrals, and with that, the interacting part independent, and basically absorb all of the relativistic components in the one-body part. Here's a typical example. This is silver iodine, where you see on the left simulation that has, this is again a fully self-consistent GW simulation that has silver iodine on the left without spin-orbit coupling, and on the right with spin-orbit coupling. You can see immediately that the spin-orbit coupling here, for example, splits some of these bands, lowers your degeneracy, and gives you very nice spin-orbit coupling effects that you really need to have in your calculation in order to do these things precisely. Anyway, all of this is only low-order perturbation theory. It is just first-order perturbation theory in the renormalized interaction, right? That's what GW after all is. We can do second-order perturbation theory. The results are remarkably similar, we find that the exchange term almost always actually matters quite a bit. So that's a dynamical exchange term, not the Fock exchange term. And so it's clearly important to add correlations to your calculations. A very simple way of doing that is just, to go and find a couple more diagrams. Down there, you see the weak coupling GW series. That's the series of polarization diagrams that we can just sum up with a GW, with a geometric series. That gives you a GW solution. You can also see two variants of the T matrix approximation just below. Those are different classes of diagrams that you could think might be important or might not be important, depending on the situation. But you can certainly write down geometric series to sum those up. And in fact, you can take all of those geometric series and just combine them together and get, the most possible diagrams that you can formulate without explicitly going to vertex functions that are dependent on more than one frequency.
So Emanuel, just one question here.
Yeah.
You are talking about right now diagrammatics in a realistic basis with many orbitals per unit cell, right?
Yes.
Which is much more challenging. But I assume that the question of, at what level does this diagrammatic expansion converge and works for a one-man model has been benchmarked in the past. Now, can you actually comment on that part?
Well, you'd think so, but unfortunately, you're mistaken. So there's actually very little done on benchmarking how well these approximations work. If you can just be patient for 2 slides, I'll show you actually some results that show how well they work at a typical example.
I just have one comment here. I don't, so you're right. I don't think I've seen these papers, and I always was curious about this. But one thing this is my impression, that if you do a GW flex or whatever parquet, from the, take a Hubbard model half-filling, and you know that even the paramagnetic phase, it can open a gap, let's say at finite temperature, some gap will open even if you don't have magnetic order at large U. But if you do flex and things like this, I shouldn't say at finite temperature, they will not be able to open a gap. That's my general impression, is that this kind of, and there's a simple reason for this, which I don't want to discuss now, but that part I think has been benchmark, right? The fact that it's hard to open a gap in a paramagnetic phase.
So yes. So Vlad, just to stop you here, yes, but the 2D Hubbard model is an exceptionally difficult model. So you could hope that in a much simpler context, some of these things might actually start to work. It's a hope, right?
Even in high dimensions.
Well, let's go to 3D, to the 3D Hubbard model.
Yes.
Right. So let me just continue, and okay. I think our opinions are actually remarkably similar on this stuff. Let's just, rather than doing it for silicon, let's just do it for the 3D Hubbard model. The reason why I'm doing it for the 3D Hubbard model rather than for silicon is because for the 3D Hubbard model, we have the exact solutions. Out of QMC DCA calculations, they are converged. They have been tested very well with different approaches. We know exactly what to expect. We actually know that there is a phase transition, a magnetic phase transition that goes from a high temperature paramagnetic phase to a low temperature antiferromagnetic phase. That's all that is happening in that model. And we can just see how well these things actually work in practice. Here's GW. Look at the arrow. The arrow is the Monte Carlo solution that we're getting. And again, these things are relatively old and they're very well known. GW gets a magnetic phase transition. It is clearly a second order phase transition. You see the inverse susceptibility here. So when it touches 0, the susceptibility diverges, right? And, maybe you're off by 25%. So what do you expect from a first order perturbation theory, right? I mean, it's good enough for that. Here's second order perturbation theory in the Baire interaction, GF2. Everything, of course, is self-consistent because at finite temperature, if it's not self-consistent, it doesn't make much sense. You can see that GF2 does not have a geometric series. If you don't have a geometric series, you can't diverge. And therefore, rather than getting a continuous phase transition, you're getting a jump to a first order ordered phase. In fact, you can see coming down from high temperature, the expected phase transition location is actually wrong, right? You can't just take your susceptibility and extrapolate because you're preempted by that first order transition. And then there's an ordered phase that actually, very nicely here gives you you know, a TC that is about as bad as the one from GW. All right, it's only second order perturbation theory. So what do you expect, right? One of the things that you can do is say that this is a magnetic system. So clearly we should have magnetic fluctuations, and it is the magnetic ladder that provides us with the T matrix for the magnetic fluctuations. Now that is at least what you're going to hear when you talk to a classically educated many-body theorist. And indeed, what you're finding is that, no, that's not the case. The results just got way worse. The susceptibility here that you're getting from high temperature that you could in principle extrapolate to low temperature is way off. Again, it is preempted by a first order transition, even though we now have one geometric series that could in principle cause that phase transition. That's not actually what's happening. And so here's a first sort of warning flag. Whenever you're doing these partial summation methods, you can't just take the susceptibility and extrapolate it to low temperature and hope for a TC. It may always be preempted by a first order transition. So you got to check the ordered phase and come from the ordered phase up in temperature to see where your TC is. And the thermodynamic TC may be very different from what you would expect just by extrapolating susceptibility.
How come TC is higher here? This is when you look at
why not? I mean, these things are totally uncontrolled.
Right. Exactly. Exactly. More diagrams doesn't mean anything. Right.
Yes, but what I'm saying you is that the traditional many-body lore that you should take magnetic fluctuations and you'll get the magnetism right is just totally not right. Don't do that, right? Don't do it. You know, superconducting ladders, well, we didn't expect much from it, but indeed there is no phase transition and there's no ordered state. If we take all of these together, miraculously, we're going to get much closer. There are actually large convergence issues in here, but you can see that there's something here that is, you know, a little bit closer to the exact result, which again is the arrow that we had over here. So what that shows you is that just adding more diagrams in a weak coupling sense is a really bad idea. This is in, you know, it's U of 6t, so this is outside the mathematical weak coupling regime. It's also outside the regime where you would typically expect weak coupling to work. If you go much lower in temperature, the correlation lengths become much longer. The things become much more difficult, and nothing actually objectively improves. So this is just a dangerous way to do physics, and you should stay far away from it. One last word of warning is about this extrapolation of the susceptibility. We see here from the high temperature and from the low temperature phases, the extrapolation of the phase transition. And that's typically how you would do high temperature perturbation theories and then look at susceptibilities and extrapolate them, or extrapolate the leading eigenvalues of the pair field susceptibilities. That's not right. Because you have this first order coexistence in these methods, these things are preempted. And therefore, the TCs that you're getting in this way are not the actual thermodynamic TCs that you'll get in reality.
And what if you do DMFT or EDMFT? I know that EDMFT can be very accurate in some cases.
All right, just, you know, give me a little bit. So I'm just telling you that this is a good approach on paper, but if you check how well it performs in practice, we have not found the killer app for it. This here clearly shows you the dangers of it. I think that's about as much as I want to say for these infinite partial summation methods. All right. And so, Vlad, as you say, right, that this is not the only hierarchy that we have. We can do more than just throw more diagrams at the problem. And so what I want to do now is show you a little bit more of a successful hierarchy where we can actually do real materials calculations for strongly correlated systems in a more or less controlled way. And I'll make that very precise. And so the idea is, of course, that we have a weakly coupled background where we do GW or second order perturbation theory or something like that. And then we select certain orbitals which are believed to be strongly correlated. And we add strong correlations onto those orbitals. So we have strongly coupled substates or strongly correlated substates, which are small, where we solve the physics exactly, which we then embed into weakly correlated environments where we have large system size, and which we can solve approximately by, you know, self-consistent GW or similar things. Now, again, we need full self-consistency in our weak coupling methods for that, so that when the local system rearranges itself and rearranges the environment via the Dyson equation, the weak coupling methods get to know about that, and the weak coupling methods or the weak coupling part or the weakly coupled orbitals and the strongly coupled orbitals talk to each other via that self-consistency to get a charge relaxed system. That is something that is missing in most of the GW plus DMFT or DFT plus DMFT systems. So anyway, so we take a system, we split it into a weakly coupled background and strongly coupled orbitals. We solve the background approximately within a weak coupling method. We solve the strongly correlated orbitals exactly, and then we use self-consistent diagrammatic theories for the feedback between the two. For models with local interactions and a mean field background, that just simplifies to weak coupling plus dynamical mean field when the correlated subspace is chosen to be strictly local. All right. So the non-perturbative solution of the correlated subspace, that is just a solution of a quantum impurity model. And fortunately, we have fast and numerically exact quantum impurity solvers that we've tried for many years, and we know exactly how they behave. The coupling to the environment appears as retardation effects or as a hybridization in this context. And if you want to, you can look at the methodology as an approximation of the exact Longrange word functional of the crystal, where you take the entire word functionals or the entirety of the diagrams that only have local indices in some correlated orbital subspace, and you supplement that with weak coupling orbitals everywhere, or weak coupling diagrams everywhere. You can then approach the exact limit by ramping up the number of diagrams in the weak coupling background. You can approach the exact limit by enlarging the correlated orbital subspace. And of course, all of this is fully ab-initio because only the choice of the basis and the choice of the correlated orbitals are required as input. And then, once you've specified your method, once you've specified your phi functional, that's essentially a self-consistency solution that you have to solve. Here's an example of that, of how that actually works. This is strontium manganate. Strontium manganate is a cubic perovskite. If we do that within GW, then you can see that at the Fermi energy, you actually get a density of states. So this is a metal within GW. We sort of know where the correlations should be in that system. Manganese T2G is probably a good place to start. And if we now go to the ab-initio system and we say we want the exact solution on the manganese T2G and only a GW solution everywhere else, and we solve the whole thing self-consistently, then the manganese T2G make the whole thing insulating. And as we then add correlations on other orbitals, for example, on the manganese EGs and the oxygen 2Ps and so on, as we add more and more of these correlated orbitals, you can see that basically not that much changes, and we converge the system to where it has to be. Again, self-consistency between the strongly correlated part and the weak coupling part is absolutely essential over here, because as you're adjusting the strongly correlated manganese T2G manifold, your GW relaxes the charge in the other orbitals and makes the whole system insulating. Here's a different case. This is strontium vanadate. This is a typical quasiparticle peak metal or a strongly correlated metal. You have vanadium here. Vanadium T2G builds a quasiparticle peak. You can see it here at the Fermi energy on the right. And basically, if we just do self-consistent GW, we get some sort of peak, but mainly we get a peak somewhere else. If we then gradually add more and more orbitals to our correlated space, we get something that once we add the vanadium T2Gs converges to a nicely correlated metal. And then as we add other orbitals to the strongly correlated subspace, you can see that basically not that much changes anymore. And these things relax to a steady state. So that shows you now that, for these very simple correlated materials, we can actually get a solution that, is, first of all, very well defined in terms of just 1960s many-body theory and, an initial basis set that you specify, and that from that point on is basically hands-off. All right. So those are embedding theories. And with those embedding theories, we can now do a whole, set of, realistic systems, basically hands-off. Of course, because our toolkit is relatively expensive computationally, we are by no means at the level that, current DFT codes or even current, so-called GW codes are, just simply because our electronic structure toolkit is relatively primitive, and also because we're working in, old quantum chemistry basis sets that we've chosen essentially for convenience, and again, because they're very well specified and essentially very much hands-off. But one of the, interesting things that we have here is that these embedding theories seem to be very powerful. And so I want to show you just how powerful they are in a very simple example where we solve now the entire system with an embedding theory. So we're basically making an approximation to the self-energy rather than an approximation to the Green's function, just to examine finite size effect in these systems. The exercise here is that we're looking at a finite system. In this case, it's going to be a Hubbard model and an extended Hubbard model in an interacting background. We truncate this system that we're looking at exactly to, on the left, 18 sides, and then on the right, you see all the way up to 100 sides. And we want to check how this works in systems that have very large correlation lengths. Now, the best way to get a system that has a very large correlation length is to take a boring system that you can actually understand very well, like the three-dimensional Hubbard model, and to just tune that system to a place where the correlation length diverges, second order phase transition, right? And that gives us a good way of now studying how we can get finite size effects on the control in these methods, and also to adapt that toolkit then to the realistic many-body simulations where we can do much more with it. So back to the simple lattice models with local interactions, with exact solutions, we know exactly what to expect. And let's see how well this compares for controlling finite size effects. Here is what the typical density functional theory community does. And let me just wait here for a second. I'm trying to get my pointer back so that you guys can actually see where I'm pointing. I think it's hopeless. It doesn't want to come back. Anyway, you see the arrow there. What you have here is the way that a typical electronic structure calculation on a three-dimensional solid would be done. You choose typically a Moncourse-Puck grid, 4x4x4, 6x6x6, 8x8x8, 10x10x10, and then maybe you go bigger, and you just observe convergence of your quantity that you care about as a function of inverse system size. You have exactly this plot over here. Again, it's the anti-ferromagnetic three-dimensional Hubbard model. What we care about here is TC. And you can see that if we give up the strict requirement that we have Moncourse-Puck grid and we allow to break some of the spatial symmetries, we can actually get many more clusters, especially at low system sizes. These are the so-called Betz clusters. If you look at the geometries of these clusters, then rather than being simply cubic x by y by z, they're now funny skewed clusters. And if you're familiar with the DCA literature, you have seen these in other contexts. Basically, you can see finite size effects are pretty severe on these systems. Moncourse-Puck grid here is one of those clusters. This is all solved within GW, so we can go to very large system sizes. But what I want to show you here is that we can now use embedding constructions like the DCA, solve exactly that system, but use the Dyson equation to generate long-range correlations, and that's what we're getting. Those are now the systems solved on much, much smaller clusters. And you can see that even at the smallest cluster size, those things are actually perfectly converged within the cluster size that we have. And so we can get away with a numerical effort that is much, much smaller than what you're having in sort of the classical electronic structure simulations.
So Emanuel, can you put this in perspective? Because for the classical models, like classical Ising model, this has been done many, many decades ago. This issue of convergence of cluster estimates. And of course, TC depends, but what is well known for the 3D Ising model, for example, is that the moment you do two cluster, like Bethe did, you get almost 99% accuracy for TC, not for the exponents though, which is a separate issue. Can you just put this in perspective? I mean, how much of this is a quantum effect versus just an effect of inter-site correlations?
So I don't know the difference between quantum effect and inter-site correlations here. This method has nothing to say about it, right? This is just GW solved on a cluster for an anti-ferromagnetic model that just has some correlations. What you need to make this work is a method that can give you an approximation to the self-energy rather than an approximation to the Green's function or the density matrix, right? So you need some sort of diagrammatic background for these things. If you look at the standard electronic structure methods, which everybody uses, right? These are formulated on the level of density matrices or on the level of Green's functions. They're not formulated on the level of the self-energy. So we don't have a good way of making a system truncation on the self-energy or a correlation length truncation on the self-energy, which is what DCA really is doing, and then using the Dyson equation to propagate Green's function correlations for much longer distances, right? That's really what's happening here. And so, yes, you're right. Within the DCA community, it's been known for a very long time that DCA converges much better than any sort of finite lattice calculation, right? And in fact, when back in the days when we did these 100-site, CTQMC DCA clusters, it was very clear that, our result would just be very nicely on an extrapolation curve. And with any sort of, finite lattice QMC calculation, you would be able to do larger lattices, but you'd suffer from these shell effects, which you see exactly here. In fact, let me go to the next plot where you see that the same thing much better. So this here, we reduced the interaction strength a little bit. You can still see we go to about 1,000 lattice sites. You can see that this is something where you have problems extrapolating TC from just Moncourt-Puck grids, right? Things are oscillating a little bit. Well, actually, things are oscillating a lot. This is now solved on all of these other Betz clusters. So what you can see here is that this is really a finite system truncation, not an effect of a bad cluster or something like that. It's really an effect of a truncation of a correlation length that you have because you just have only so much space for fitting your system. Now, on the level of these embedding theories, you don't care. Here's your result, right? That these finite size effects are simply gone because you have a self-energy equation or a Dyson equation that takes your self-energy and with that geometric series generates the long-range equation, the long-range correlations that are exactly the ones that you needed over here. Now, in practice, of course, we would never believe that. But what we can do is we can simulate a sequence of these systems, of these system sizes, and then just simply look whether our finite size effects are gone or still present. But it allows us to get away with, underneath it all, simulating much shorter range correlations than what we would have to do.
The single site approximation is still off. I mean, it sounds like here there is no finite size effect. Obviously,
no. Look at the y-axis, right? There's no single site in any of this. So this is the linear cluster size, and I actually forgot what the smallest one is, but it's certainly not a single size site.
But you agree the single site should be off, right? Because the rest.
Oh yeah, totally. No, in a single site you don't have any non-local correlations, and you need some non-local correlations to see the.
So that is consistent with what I said. The moment you put two-side correlations, you're basically done, right?
Yeah. Well, so is this a very special case? Maybe. Right? We tested this case as a case that is notoriously difficult for these finite size convergences. Whether that's the same in a real material or not, we're actually testing this at the moment. But it is certainly a very powerful methodology that allows you to get away with simulations on quantum simulations on much smaller systems that then can be put into a Dyson equation in order to get long-range correlations that suffer.
Emanuel, I think you are here. This people, field theorists, will be very upset with what you said because Wilson taught us that physics comes from long distances and not from short. If you're interested in critical exponents, if you're interested in the value of TC, which is not universal, then sure, you don't have to do a large system size. You can do 2 or 3 cluster, and then you're done. So focusing on TC as your only criterion for success in terms of the finite size effect is totally missing all the infrared physics of the collective mode. Obviously.
Well,
you will agree with that. Right?
So no, Flot, you're missing the point here. So that is not a result for TC as much as it is a methodology that tells you how you should do these extrapolations. And what it tells you is that you can get a very regular conversions here. By observing how these things work, within an embedding scheme. It is much more powerful to do it in the embedding than without the embedding. Now, if you have more finite size effects that are longer range, fine. Your curve here will look different, and we will have some trend in it. And then the question is, are you either converged with that trend to within the precision you care about, or is the trend regular enough that you can extrapolate from it, right? Okay. In any way, you can get away with many more points on much smaller systems. And remember, all of these equations are expensive to do on large system sizes. The smaller you can do it, the better you are off. Right. Anyway, so I agree with you that there are subtleties, and if you want to get the critical exponents, which is not something I would ever want to get, you're in trouble with all of these diagrammatic methods. But you can still extrapolate, and you still have something that eventually will be right. And whether you're right with the calculation that you have within the precision you care about, that will depend on an extrapolation plot like this one. And so you just got to do it. All right. So yeah, you can see here that even on these small system sizes, we're actually getting very nice results. When we're looking at k-dependent quantities like k-dependent spectral functions and similar things, there are also a couple other technologies that we can try. Periodic boundary conditions is the obvious one. We can try twisted boundary conditions, which basically means introducing a slight phase in your hoppings that shifts your k momentum points. Or we can try DCA. And you can see here that, well, this is perhaps, I think I need a better plot for that, but you can see again that DCA for the convergence for these systems is actually much, much better. It's much, much more regular and really gives you a nice way of getting results for much larger systems based on a quantum solution of a much more confined system. All right, I should slowly come to the end. So where do we stand with all of this stuff? I would say, we have now a solid foundation to perform many-body theory ab initio without additional adjustable parameters and reproducibly. Basically, we specify in a paper what our basis functions are and what our methodology is, GW, GF2, and what our correlated orbitals are. And at that point, that result is basically, anybody else should be able to get the same result. The leading error, and that's something that we observe very often, is the weak coupling approximation. All of the other approximations, like finite size, basis set, DFT starting point dependence, and so on, are either eliminated or they're under control. And that now allows us to have discussions about, diagrams that are missing or that should be in there, or orbital subspaces that are either correlated beyond that or not. I showed you very tangentially that we can do all of this relativistically. So spin-orbit coupling is actually really important. None of this has adjustable, L.S parameters that you throw in after the fact. This is just by solving the Dirac equation. I showed you that increasing the diagram order is just not a way forward. It's really dangerous. We can do it technically. In fact, we can do it for realistic materials, but it just looks like it's not a good idea. Embedding is remarkably powerful. It works both in models and in realistic systems. It is technically expensive, and we have the toolkit for that. It's improving rapidly, but of course, we're nowhere near sort of production-ready DFT simulations where you just, basically enter your system and run. There's still a very long way to go for parameter-free ab initio methods for strong correlation. And so I want to come back to sort of these hierarchies, right? I started out by saying that any numerical mathematician who considers an algorithm really would like to have, error bounds and error methods and hierarchies that are convergent as you increase complexity. Every additional step should add complexity, but should also get you closer to the exact result. Adding these infinite summations of diagrams clearly was not the way to go, right? But we have plenty of other hierarchies that we can go for, right? System sizes, diagram types, entanglement, diagram orders, embedding subspaces, basis sets, and so on. And so, if you're thinking of the meme of the Jacob's ladder that's sometimes used in a DFT where you go one rung up and you get a little bit closer to that, I think, we're closer to defining some of these hierarchies now also for strongly correlated systems. And so again, where do we stand? I think even in the absence of full control and convergence, we have a new generation of embedding methods that is predictive, as in we can't tune at any place, our results are just whatever they are. They are reproducible. There's a minimal set of parameters that we need to specify, and that is very different from many of the strong correlation calculations that you see out there. So for example, double counting corrections, vanillization intervals, basis set dependence, interaction choices, solver approximations, starting point dependencies, if you have not a full self-consistency, truncation of certain off-diagonal elements of the self-energies or Green's functions. Those are all things that are done routinely in present-day calculations that we manage to eliminate. The types of things that we're doing are very well defined in terms of strict diagrammatic many-body perturbation theory. You can essentially go back to the 1960s, open a textbook or one of the original paper, and you find the equations there. It's all formulated at finite temperature. And with that, we can say something about phase transitions, entropy, and grand canonical effects. And because it's in a Green's function language, I don't need to say that here, it's actually very close to experiment, formulated directly in terms of fermionic and bosonic response functions. All right, so with that, I would like to thank Gianni, Gianna, and Sergey, as well as the group of Dominica, and thank you all for your attention.
Thank you. That's a very nice talk. So we open the floor to everyone for questions. Let me stop recording. So whatever you say will not be showing public.